So in the last video, I described how to interpret three-dimensional graphs. And I have another three-dimensional graph here. It's a very bumpy guy. And this happens to be the graph of the function f of xy is equal to cosine of x multiplied by the sine of y. And I could also say that this graph represents z is equal to that whole value, because we think about the output of the function as the z coordinate of each point. And what I want to do here is describe how you can interpret the relationship between this graph and these functions that you know by taking slices of it. So for example, let's say that we took a slice with this plane here. And what this plane here is it represents the value x equals 0. And you can kind of see that because this is the x-axis. So when you're at 0 on the x-axis, you pass through the origin, and then the values of y and z can go freely. So you end up with this, this plane. And let's say you want to just consider where this cuts through the graph. Okay, so we'll limit our graph just down to the point where it cuts it, and I'm going to draw a little red line over that spot. Now what you might notice here, that red line looks like a sinusoidal wave. In fact, it looks exactly like the sine function itself. It passes through the origin, it starts by going up, and this makes sense if we start to plug things into the original form here. Because if you take f and you plug in x equals 0, but then we still let y range freely, what it means is you're looking at cosine of 0 multiplied by sine of y. Sine of y. And what is cosine of 0? Cosine of 0 evaluates to 1. So this whole function should look just like sine of y, in that when we let y run freely, the output, which is still represented by the z coordinate, will give us this graph that's just a normal two-dimensional graph that we're probably familiar with. And let's try this at a different point. Let's see what would happen if instead of plugging in x equals 0, let's imagine that we plugged in y equals 0. And this time, before I graph it and before I show everything that goes on, let's just try to figure out, purely from the formula here, what it's going to look like when we plug in y equals 0. So now I'm going to write over on the other side, we have x will still run freely, y is going to be fixed at 0. And what this means is we have cosine of x, so maybe you expect to see something that looks kind of like a cosine graph, and then sine of 0. Except, what is sine of 0? Sine of 0 cancels out and just becomes 0, which multiplied by cosine of x means everything cancels out and becomes 0. So what you'd expect is that this is going to look like a constant function that's constantly equal to 0. And let's see if that's what we get. So I'm going to slice it with y equals 0 here. And we look at the y-axis, we see when it's 0, and x and z both run freely. Then I'm going to chop off my graph at that point. And indeed, it chops it just at this straight line. The straight line that goes right along the x-axis. But let's say that we did a different constant value of y. Rather than y equals 0, so rather than y equals 0, and we'll erase all of this, let's say that I cut things at some other value. So in this case, what I've chosen is y is equal to pi halves. And it looks kind of like we've got a wave here. And it looks like a cosine wave. And you can probably see where this is going. This is when x is running freely. And if we start to imagine plugging this in, I'll just actually write it out. We've got cosine of x, and then y is held at a constant, sine of pi halves. Sine of pi halves is this just always equals 1. So we could replace this with 1, which means the function as a whole should look like cosine x. So again, the multivariable function, we've frozen y, and we're letting x range freely, and it ends up looking like a cosine function. And I think a really good way to understand a given three-dimensional graph when you see it. So, let's say you we look back at the original graph and we don't have anything going on. Get rid of that little line. So you've got this graph, and it looks wavy and bumpy and a little bit hard to understand at first. But if you just think in terms of holding one variable constant, it boils down always into a normal two-dimensional graph. And you can even think about, as you're letting planes kind of slide back and forth, what that means for the amplitude of the wave that you see, and things like that. This becomes especially important, by the way, when we introduce a notion of partial derivatives.